All right, so here's the next example of finding exact area using our summation. So this time we're looking for the exact area under the curve of f of x equal to x squared plus 2 on the interval from 1 to 4. So I'm actually going to write this as an integral. So we know that we're looking for the integral starting at 1, ending at 4 of our function, which is going to be x squared plus 2 dx, which again is equivalent to the limit as n is approaching infinity of our summation from our first subinterval to our nth subinterval of f of x sub I times delta x. So our initial information here, again, we're not sure about our number of subintervals, so we're not sure about n because, again, we're approaching infinity there. Our delta x is going to be our b minus a divided by n. So b minus a would be 4 minus 1 divided by n is going to give me 3 over n. Our x sub I this time is going to be a little bit different because our starting x value here is 4. I'm sorry, is it 1? And then I'm going to add to that our delta x, which is going to be 3 over n, and then times I. So this is actually going to be our x sub I, so we can't actually simplify this any. And then I know that in order to plug in over here, I need to know what my f of x sub I is. So I'm going to go ahead and I'm going to plug in this x sub I into my function up here. So this is going to be 1 plus 3 over ni squared, and then plus 2. So this I have to be a little bit careful about because I do have a sum on the inside of these parentheses. So in order to square it, I am going to have to multiply that out. So 1 plus 3 over ni times 1 plus 3 over ni, and then plus 2. So I'm actually going to go ahead and FOIL this out. So that's going to give me a 1. If I FOIL out these outer terms, so 1 times 3 over ni is 3 over ni, and then I get the same thing on the inside here, 3 over ni. So what I'm really adding to that is going to be 2 times 3 over ni, because I have 2 of them. And then when I multiply 3 over ni times 3 over ni, I'm really multiplying the numerators. So 3 times 3 is going to give me a 9. Denominator n times n is going to give me n squared. And then when I multiply my I times I am going to get an I squared here. And then I can't forget to bring down that plus 2 on the outside here. And then I'm just going to combine some like terms and kind of clean things up a little bit. So that's going to give me a 3 when I combine together the 1 and the 2 here. When I multiply 2 times 3 over ni, that's going to give me a plus 6 over ni. And then plus 9 over n squared I squared. So this is my f of x sub I right here. So this is going to be the quantity that I want to bring up and substitute into my formula up here. And then the delta x, we calculated over here to be 3 over n. So my limit as n is approaching infinity of my summation. So I'm going to go ahead and bring this over in brackets. I'm going to multiply that by the 3 over n. Okay, so when I multiply this 3 over n out, I am going to just kind of be careful with this first term, and you'll see why when I go to use those formulas that we were talking about to help us kind of substitute in for some things. So you'll kind of notice that I'm going to leave something for right now. So I'm going to multiply this out. So I'm going to leave that as the limit as n is approaching infinity. I'm going to go ahead and bring over my summation. So when I distribute out the 3 over n, I am going to need to make sure that it's getting to all 3 terms here. But when I multiply it by this constant, I'm going to actually leave it as 3 over n times the constant of 3. And again, you'll see why in a second. But I am going to go ahead and multiply this out. So 6 times 3 over here is going to give me an 18 over n times n is n squared. And then I'm going to bring over the I in that term. And then when I multiply this to the 9 term, that's going to give me a 27 over n to the third, and then I squared. So the idea kind of is the same here. So I'm seeing that I have terms with I and I squared this time. Our last example only had an I squared. So this one does have another term that we're going to have to kind of deal with. And we have a constant. So we have a constant, we have an I term, and we have an I squared term, which actually means we're going to want to use 3 of these things to substitute in for. We're going to want to use the thing that I was talking about today with the constant. We're going to want to use the one that's got the I, and we're going to want to use the one that's got the I squared here. So we're going to actually have 3 things to substitute in for. But what I'm going to do is I'm going to kind of manipulate this a little bit to get it into the form that we need to in order to substitute in for. And what I can do here is I can actually break this into 3 separate summations. So I'm going to break this into the limit as n is approaching infinity. And each one of these terms are going to get their own summation. So I'm going to break this into the summation of 3 over n times 3 plus the summation of 18 over n squared times I plus the summation of 27 over n cubed I squared. And what I'm going to do in each one of these cases, because I know I have, like I said, a constant, I know I have an I, and I know I have an I squared that I can plug in for. What I'm going to do, and the reason that I did not multiply this out together, is I'm actually going to go ahead and pull out this 3 over n to the outside of the summation, where I'm just going to be left with a constant, so then I can substitute in. I'm going to go ahead and do the same thing with the 18 over n squared, and I'm just going to leave the I here, and I'm going to do the same thing with the 27 over n cubed, and I'm just going to leave the I squared with the summation. So I'm going to bring down my limit, write this as 3 over n times the summation of just my 3, plus bring over the 18 over n squared times the summation of just my I, and then bring out the 27 over n cubed of my summation of my I squared. And at this point, I've gotten into the place where I can use what I know to substitute in for this term, substitute in for this term, and substitute in for this term. Because now I've got something that looks exactly like the formulas that we were talking about earlier. So this one we just have to be a little bit careful about, but we know that this I is just equivalent to this n times n plus 1 over 2. This I squared is equal to this stuff, which we saw in our last example. So when I go to plug in for my constant term here, we said that the summation of a constant, which our constant is 3, is going to be equal to n times whatever the constant is. So since my constant is 3, my summation is going to be equal to 3n. So again, since we're just dealing with a constant here, my summation of any constant is equal to n times whatever the constant is. So since my constant is 3, my summation is going to be equivalent to 3n. And then I'm going to go ahead and bring over the plus 18n squared, or 18 over n squared. And I'm going to go ahead and substitute in for what I know about that. So I know that the I summation is equivalent to n times n plus 1 over 2. And then I'm going to bring over the plus 27 over n cubed. And I'm going to go ahead and substitute in what I know about the summation for the I squared, which is equivalent to all this stuff. So n times n plus 1 times 2n plus 1 all over 6. And similar to what I did in the last problem, I'm going to go ahead and simplify this, or kind of clean things up a little bit. So I'm going to kind of get rid of any n's that I can, and then I'm going to go ahead and multiply out what I can't get rid of. So I do have an n here that's going to cancel with my first term, so I'm left with the limit as n is approaching infinity of, I should be just left with a 9 here. Plus, I should be able to get rid of one of my n's, as well as I can actually simplify this 18 divided by 2. If you want to do that in the next step, you can, if you prefer. So if you want to just leave this as 18 times the quantity of n plus 1 all over And then in the denominator, we're still left with a 2n. And then here, I'm going to get rid of one of the n's again. So this is going to become an n squared in the denominator. And again, you can definitely simplify with that 6 as well, which I didn't do in the last example, but you can if you want to. So I'm left with the 27 times n plus 1 times 2n plus 1. And then the denominator, I'm left with a 6n squared. And then I'm just going to kind of clean things up a little bit here, just so it's a little bit easier to work with. So like I said, if you want to clean up kind of the coefficients, so here these have a common factor of 2. So I would be left with a 9 in the numerator here. So this would leave me with a 9 plus, and then I could go ahead and actually distribute that 9 out in the numerator. So 9n plus 9. And then I'm still left with a denominator of n here. Don't forget that the n is still in the bottom there. And then I can simplify this. I can divide each one of these by 3. So I think that leaves you with a 9 in the numerator and a 2 in the denominator. So I'm going to bring over the 9, and I'm actually going to multiply these two out. So that's going to give me a 2n squared plus 3n plus 1 again. And then I'm left with a 2n squared in the denominator. And then I'm just going to kind of start cleaning things up a little bit here. So bring down the 9, and then I'm going to separate this fraction because we kind of clean things up over here. So I'm going to separate that fraction into each denominator of an n. So 9n over n plus 9 over n. And then I'm just going to kind of clean things up a little bit up here so I can still distribute out the 9. So it's going to give me an 18n squared plus 27n plus 9 all over 2n squared. And then I'm going to separate these out to be their own fractions so that I'm able to take the limit as n is approaching infinity. And I'm just going to clean things up a little bit as I go because I can see in this second fraction here, my n's cancel out, so I'm just left with a 9. And then I'm left with an 18n squared over 2n squared plus 27n over 2n squared plus 9 over 2n squared. I can kind of do a little bit of simplification, a little bit of cleaning up here. So I'm going to combine these. So 9 plus 9 is going to give me an 18. I'm left with a plus 9 over n. Here, my n square is actually canceled. I'm left with an 18 divided by 2, which gives me another 9 here. I can get rid of an n here, so that leaves me with a 27 over 2n. And then plus 9 over 2n squared. And now that I've kind of cleaned things up a little bit, you can combine the 18 and the 9 if you want to, but I'm just going to go ahead and just take the limit as n is approaching infinity of each one of these fractions. So limit as n is approaching infinity of 18 is just 18. Limit as n is approaching infinity of 9 over n goes to 0. Limit here as n is approaching infinity is just going to be 9. And then these two both have variables in the denominator, so both of these are just going to go to 0. So that leaves me with an 18 plus 9, which is going to be 27, which is actually representing the area underneath the curve of x squared plus 2 from the x value of 1 to the x value of 4. So that is our exact area under the curve. So these two examples that I just did will help you out with the homework problems. Let me know if you have any questions about anything.